Section 1 Introduction. We're here to introduce our work on large language models, LLMs, which are powered by transformers and have shown significant progress in a wide range of natural language processing, NLP, tasks. As these models grow in size and training data, they're becoming more adaptable and less task-specific, opening up new possibilities in solving complex AI tasks. These tasks range from answering questions and generating code to reasoning, solving math problems, and even understanding humor. LLMs are capable of capturing a wealth of conceptual knowledge about the world through their lexical embeddings. This leads us to wonder, if we feed these models with suitable visual representations, could they solve tasks in visual modalities? Recently, there have been significant strides in expanding the capabilities of LLMs to handle image understanding and retrieval tasks. However, it's been a challenge to generate a different modality using an LLM that hasn't been explicitly trained on that modality. To help LLMs with such cross-modal tasks, we suggest learning a vector quantizer to map an image, or any other non-linguistic modality, to the token space of an LLM. This essentially translates the image into a language that the LLM can understand, allowing us to use the LLM's generative abilities to perform conditional image understanding and generation tasks without needing to train on image-text pairs. Our new approach involves taking an image prompt, converting it to a token space with our learned encoder, using the LLM to generate suitable lexical tokens, and then converting back to pixel space with our learned decoder. We've developed a new Semantic Pyramid AutoEncoder, SPAE, that produces a lexical word sequence that carries rich semantics and retains fine details for signal reconstruction. Unlike most VQ-VAE approaches, our encoder maps to a discrete latent space that is interpretable, i.e., words. Our SPAE tokens have a multi-scale representation arranged in a pyramid structure. The upper layers of the pyramid contain semantic central concepts, while the lower layers prioritize appearance representations that capture the fine details for image reconstruction. This design allows us to adjust the token length dynamically to suit various tasks. We've tested our approach in an extreme setting of in-context learning, without any parameter updates to the LLM. Our SPAE model is trained standalone, without backprop aggregating through any language model. We've evaluated our approach on image understanding tasks including image classification, image captioning, and visual question answering. We've also demonstrated the image generation capabilities of LLMs by using in-context denoising techniques. Our method is LLM agnostic and has been tested with PaLM 2 and GPT 3.5, suggesting compatibility with any LLM. The main contributions of our work are as follows. 1. To the best of our knowledge, this is the first successful method that uses a frozen language model, trained solely on language tokens, to directly generate image content through in-context learning. 2. We've introduced a new SPAE tokenizer that produces interpretable representations of semantic concepts and fine-grained details in the form of multilingual linguistic tokens with adjustable lengths. 3. We've proposed a new progressive prompting method that facilitates in-context generation of long cross-modal sequences. 4. We've evaluated our method on visual understanding and generation tasks, and notably, our approach outperforms the best published few-shot image classification accuracy by an absolute 25% under the same in-context setting. We will make our code and models available for the purpose of reproducible research. Section Summary. Large language models, LLMs, have made significant progress in various natural language processing tasks, but their ability to handle visual modalities is limited. To address this, we propose a method that maps images to the token space of a frozen LLM, allowing us to leverage the generative abilities of the LLM for image understanding and generation tasks. We introduce a Semantic Pyramid AutoEncoder, SPAE, that produces interpretable representations of semantic concepts and fine-grained details, enabling us to dynamically adjust the token length for different tasks. Our approach achieves impressive results in image understanding and generation tasks, surpassing the best published few-shot image classification accuracy by 25%. Section 2 Related work. We've been working on enhancing the abilities of language learning models, LLMs, to go beyond just language. 4. Instance. Visual Chat GPT uses Chat GPT to create prompts and carry out tasks that involve multiple modes, like generating images from text prompts using Stable Diffusion. Fromage uses clip embeddings with opt for understanding and retrieving images. However, it needs backpropagation through the LLM and doesn't support image creation. Our work allows a standalone, unchanging LLM to understand and generate other modes that it hasn't seen during training. We've also been using Vector Quantization Variational AutoEncoder, VQ-VAE, to compress data into a discrete latent space defined by a codebook through vector quantization. VQGAN improves the quality of reconstruction with adversarial and perceptual objectives. These discrete latent quantities, often called tokens, are widely used to learn generative transformer models for images, videos, and audio. Our SPAE model is built on the VQGAN framework and can be applied to different modes. In typical VQGANs, the codebooks are learned together with the encoder and decoder stacks, which can't be directly interpreted through natural languages. LQAE replaces the learned codebook with frozen word embeddings from BERT to connect with English vocabulary. However, the LQAE tokens rarely contain semantic concepts in an image, and the quality of reconstruction is worse than that with a learned codebook. Our SPAE turns an input sample into tokens that are semantically related in a multilingual vocabulary while maintaining the high quality of reconstruction of a VQGAN for generative tasks. Moreover, SPAE tokens are arranged in a multi-layer course-defined pyramid for flexible use in different tasks. We've also been using in-context learning to help LLMs learn from a few examples through the text interface without updating parameters. This method is often used to evaluate the performance of LLMs on many natural language processing (NLP) benchmarks, such as classification and question answering, mathematical reasoning, and code generation. It gives results that are competitive with their fine-tuned counterparts. However, existing frameworks for understanding and generating vision language still need LLM parameter updates. In contrast, our work inherits the ability to learn in context from frozen LLMs. Section summary. Advances have been made to expand the capabilities of language models, LLMs, beyond language, such as generating images from text prompts. However, these approaches require backpropagation through the LLM and do not support image synthesis. Our work enables a standalone frozen LLM to understand and generate other modalities, even those unseen in training. We build upon the VQGAN framework, which uses tokenization via vector quantization, and our model quantizes input samples into semantically related tokens in a multilingual vocabulary while preserving high reconstruction quality. Additionally, our work inherits the in-context learning ability from frozen LLMs, allowing for few-shot learning without parameter updates. Section 3 Method. In this section, we'll explain our method for transforming images, or other non-textual data like videos or audio, into a language sequence that language learning models, LLMs, can understand. We use a tool called the Semantic Pyramid AutoEncoder, SPAE, to create a sequence of words that not only carries a lot of meaning but also preserves the fine details needed to reconstruct the original signal. To make this work with a pre-trained LLM, we use a step-by-step method of removing noise from the data to help with image creation. We'll use images as an example to explain our SPAE model in 2 dimensions, and later we'll show you how it works with 3-dimensional video data. Our SPAE model builds on the Vector Quantized Variational Autoencoder, VQVAE, framework, which includes an encoder, a quantizer, and a decoder. The encoder, which is a type of convolutional neural network, CNN, transforms an image from a height by width by 3 color channels format into a continuous set of embeddings with a different height, width, and number of channels. Each of these embeddings is then processed by the quantizer, which assigns it to the nearest entry in a codebook, creating a quantized embedding. We'll use the symbol Z hat to represent the quantized embeddings for the whole image. The decoder, another CNN, takes Z hat as input and produces a reconstructed image, which we'll call I hat. Our SPAE model differs from the VQVAE framework in a few key ways. For one, it creates lexical tokens in a pyramid structure, with high-level semantic concepts at the top and progressively more detailed appearance information at the bottom. We also introduce a semantic loss to encourage the use of tokens that are relevant to the concepts being represented. To create these lexical tokens, we use a pre-trained LLM codebook and keep it fixed during training. This codebook is a set of pairs, each consisting of a subword and its corresponding text embedding, which can be obtained from any layer of the LLM. Because the codebook aligns with the language vocabulary, we can use the terms token and word interchangeably. Section summary. In this section, the authors propose a method called Semantic Pyramid AutoEncoder, SPAE, to model non-linguistic modalities, such as images or videos, as language sequences that can be understood by language models, LLMs. SPAE generates a sequence of lexical tokens arranged in a pyramid structure, with semantic concepts in the upper layers and progressively refined appearance details in the lower layers. They also introduce a semantic loss to encourage the usage of conceptually relevant tokens and utilize a pre-trained LLM codebook to generate lexical tokens. Section: Token Pyramid. We're introducing a new concept called the token pyramid. In our method, the SPAE quantizer generates D layers of tokens. In each layer, we denote the tokens as K_L, which are part of a matrix T with dimensions H_L by W_L. Previous methods used something called residual quantization, RQ, to create multi-layer tokens. However, in these methods, all tokens are the same shape and don't carry any specific meanings. We're doing something different. We're proposing a pyramid structure for our tokens. We do this by making sure that the height and width of each layer are less than or equal to the height and width of the next layer. The idea behind this pyramid structure is to concentrate the meaning within the upper layers of the pyramid. This allows us to represent complex concepts using fewer tokens, sometimes as few as 5. This is a challenge that RQ doesn't have to deal with because its tokens don't carry any inherent meaning. To select the positions for quantization at each layer, we use a dilation subsampler, denoted as P(L). The subsampler selects positions based on a formula that involves the downsample ratios H_prime and W_prime, which are calculated by dividing the height and width of the final layer by the height and width of the current layer. For each embedding Z at a certain position, X, Y, we get its discrete tokens K_L sequentially from layer 1 to D at each layer. If the position X, Y is in the set P(L), the quantizer assigns a token K_L. This token is the one that minimizes the squared difference between the current remainder embedding Z_L and the token embedding E, K. The current remainder embedding Z_L is calculated using a formula that involves the sum of the differences between the original embedding Z and the token embedding Z, K_I, for all previous layers where the position X, Y is in the set P(I). The quantized embedding reconstructed with the first L layers is given by the average of the existing token embeddings. This average is calculated using a formula that involves the sum of the token embeddings E, K_I, for all layers where the position X, Y is in the set P(I). Using the input of the reconstructed embeddings from tokens up to layer L, the decoder can progressively reconstruct the image with dynamic token lengths. This results in improved quality with refined appearance details. We call this approach streaming average quantization, SAQ, because it's similar to computing the average on streaming data. In this context, RQ is applicable but yields worse results, as revealed by our studies. This can be attributed to varying scales of embeddings in residual layers, potentially dividing the codebook into multiple parts, and misalignment in the summation of word embeddings, which undermines learning semantically meaningful tokens in later layers. Section summary. The token pyramid is a novel structure that generates multi-layer tokens with specific semantic meanings. By enforcing a pyramid shape, the upper layers of the pyramid concentrate the semantics, allowing for representation with significantly fewer tokens. The streaming average quantization, SAQ, approach reconstructs the image progressively using dynamic token lengths, resulting in improved quality and refined appearance details. In comparison, residual quantization, RQ, yields worse results due to varying scales of embeddings and misalignment in the summation of word embeddings. Section: Semantic loss. We aim to maintain the semantic similarity between an image, denoted as I, and each lexical token, denoted as K. This similarity is represented by S, I, K. During the training process, we create candidate token pools for each layer, denoted as C_L, I. These pools are made up of tokens from a set T, where the similarity between the image and the token is greater than or equal to a certain threshold, denoted as ρ_L. We set the threshold for each layer such that it is less than or equal to the threshold of the next layer. This allows deeper layers to have a larger pool of candidate tokens, even though it might mean losing some semantic similarity. We could use image text pairs to define the similarity score, S, I, K, but this would limit the use of large-scale unpaired data. Instead, we use a pre-trained model called CLIP to define the similarity score. We use the CLIP model to create embedding functions for both the image and the text, denoted as f_I and f_T respectively. We then calculate the text feature for each token, K, by averaging the text embedding function over a list of prompt templates, denoted as page during training. We extract the image feature, f_iodine monoiodide, and calculate the dot product similarity with the text feature. We then normalize this similarity score to account for differences in scale across different images. We define the semantic loss for the encoder parameters, theta_E, by taking the expectation over the layers and the candidate tokens in the pool. We randomly select semantically similar target codes for each embedding in the first D layers. We also calculate an appearance loss using an improved VQGAN objective. This loss is calculated by taking the difference between the original image and the reconstructed image, and adding the sum of the differences between the original and reconstructed embeddings for each layer. We also include additional losses from the VQGAN, perceptual, and LLM models. The appearance loss is applied to both the encoder and decoder parameters, excluding the frozen codebook embedding. To balance between appearance and semantics during training, we add a dynamic weight for the semantic guidance loss. This weight is calculated by taking the ratio of the appearance loss to the semantic loss. The total training loss, excluding the GAN discriminator, is calculated by taking the expectation over the images of the sum of the appearance loss and the weighted semantic loss. Section summary. In order to encourage semantic similarity between images and textual tokens, this paper builds candidate token pools based on a threshold value for each layer during training. To define the similarity score, a pre-trained clip model is employed, where image and text clip embedding functions are used to compute the dot product similarity. The semantic loss for encoder parameters is defined by sampling semantically similar target codes, while the appearance loss is calculated using an improved VQGAN objective, including VQGAN, perceptual, and LLM losses. A dynamic weight is added to balance between appearance and semantics in the training process. Section 3.2 Progressive in-context denoising. In this section, we delve into the concept of progressive in-context denoising. Our method is particularly effective when we use backpropagation through large language models, LLMs, by tuning prompts or adapters. However, this study aims to test the feasibility of in-context learning in an extreme setting. We show that LLMs can take on new tasks in unfamiliar modalities without any changes to their parameters. To illustrate, we feed a set of K examples into the LLM to learn a new task and respond to a query. However, using a single-pass autoregressive decoding to sample the response is not ideal due to the shift in the distribution of the representation and the presence of exceptionally long sequences. For instance, an image can be broken down into more than 500 tokens. To address this, we introduce a method called progressive in-context denoising. This involves a multi-step generation process. We denote the number of tokens generated in T steps as S_T. At each step, we sample a segment of the full sequence. The sequences are concatenated using a specific symbol. We use another symbol, C_T, to control the length of previous segments to condition on. When C_T equals S_T, it remains an autoregressive AR process, where each segment of the sequence conditions on all previously decoded segments. When C_T equals 0, it corresponds to a segment-wise non-autoregressive NAR process, where each segment of the sequence is independently sampled. It's important to note that the generation within each segment is always an autoregressive decoding procedure of the LLM. In practice, we use AR to generate the first few token layers given task-specific conditions. Then we use NAR to generate the remaining token layers conditioned on the previous layers in an unconditional latent refinement process. Section summary. The authors propose a progressive in-context denoising method for learning new tasks using language models, LLMs. They demonstrate that LLMs can perform tasks in foreign modalities without parameter updates by feeding a set of examples to the LLM. The method involves a multi-step generation process where segments of the full sequence are sampled based on task-specific conditions, using both autoregressive and non-autoregressive decoding. Section. In-context denoising. We've found that the learning capabilities of an in-context setup aren't enough to fully understand a foreign modality or a different type of data. Up until now, there's no evidence to suggest that a fixed language model can generate image content. So, we use a denoising approach to generate content. For instance, in an image-to-image task, we use images that have been randomly distorted in the token space. The distortion ratio follows a cosine schedule. To explain this in simpler terms, imagine we have a set of images. We then introduce some noise or distortion to these images. This distortion is represented by the symbol epsilon and a ratio r. The ratio r follows a pattern known as a cosine schedule. We use a tokenizer, represented by Q, from the SPAE model to convert the images into tokens. We also create a condition image by zeroing out certain pixels of the real image, like masking out the bottom half for outpainting. The query image is always sampled from a small subset of raw images without any noise. To make sure the generation isn't just copying the context, we enforce a minimum distortion rate of 20%. This ensures that no identical image from the context matches the real target image. In our experiments, we wanted to test the flexibility of our approach and its compatibility with different language models. So, we trained two versions of the SPAE model, one with the PaLM language model and the other with the GPT language model. The PaLM version uses a codebook from the input embedding layer of a PaLM2S checkpoint with a vocabulary of the most frequent sentence pieces. The GPT version uses a byte pair encoding vocabulary with 99 KUTF-8 tokens. We also trained a video-based SPAE model on the Kinetics 600 dataset. We applied a semantic guidance loss to the first 5 layers, with thresholds of 0.98, 0.95, 0.9, 0.85, and 0.8. We used the CLIP model with a VIT-L14 vision backbone. We used 80 prompt templates from the zero-shot ImageNet classification setup to precompute the CLIP text embeddings for the vocabulary. For optimization, we used the Atom optimizer with specific loss weights and a learning rate of 0.0001. This followed a linear warm-up, cooldown, and root square decay schedule. We trained the SPAE model on the ImageNet ILSVRC2012 dataset with a batch size of 256 for 450K steps. More details about our implementation can be found in the appendix. Section Summary. In the context of denoising, the learning capacity of an in-context setup is not sufficient for a foreign modality. Previous attempts have failed to demonstrate that a frozen LLM can generate image content. To address this, we operate in a denoising subspace and use randomly corrupted images as context to achieve image generation. We enforce a minimal corruption rate to ensure that the generated images are not simply copies of the context. We train 2 variants of SPAE, namely SPAE_text PaLM and SPAE_text GPT, and use different LLMs for contextual token embeddings. We also apply semantic guidance loss and use CLIP with a VIT-L14 vision backbone for additional guidance. Section. Few-shot image classification. We tested our language model's ability to understand images in context using the Mini ImageNet few-shot classification benchmark. This involved feeding the model a set of tokenized images and class labels, which it then used to classify a new image. We evaluated 14 different settings, which were influenced by 4 factors. 1. Task induction. This refers to whether we included a preamble to define the output space. 2. Number of ways. This is the number of categories. 3. Number of inner shots. This is the number of unique examples for each category. 4. Number of repeats. This is how many times each unique example is repeated. We compared our method, SPAE, with 2 other leading methods, Frozen and LQAE. Our results showed that SPAE, when using the GPT 3.5 model and in context format, consistently outperformed LQAE, despite only using 2% of its tokens. We also tested the performance of SPAE with different numbers of layers in 6 settings with task induction and no repeats. We found that SPAE with 3 layers achieved the best balance between semantics and sequence length, reducing the learning burden on the language model. Overall, SPAE improved average accuracy by 25% and 32% on the 2-way and 5-way benchmarks, respectively, compared to the best current methods. We also compared the quality of image and video reconstruction using tokens produced by SPAE and the VQGAN baseline, which is commonly used in image and video generation. We used several metrics to make this comparison, including FID, inception. Score is LPIPS for image VQGAN from mask GIT on the ImageNet validation set, and FVD for the 3D VQGAN from MAGVIT on the Kinetics 600 validation set. To measure the semantics, we calculated the CLIP and relative CLIP scores, averaged across all lexical tokens. Our results showed that, unlike VQGAN tokens, which lack specific semantic meaning, SPAE tokens had high semantic CLIP scores, especially in the lower layers. As we increased the number of layers, more tokens were used, which improved the quality of the reconstruction. This flexibility allows us to adjust the token length dynamically to suit different tasks, such as using fewer tokens for understanding tasks. While SPAE may have a higher loss in reconstruction compared to VQGAN when using a similar number of tokens, this is offset by going into deeper layers. Section Summary. The paper evaluates the performance of a frozen language and vision model, LLM, on the Mini ImageNet few-shot classification benchmark. They compare their method, called SPAE, with state-of-the-art methods and show that SPAE consistently outperforms them while using only a small fraction of tokens. Additionally, they compare the tokenization quality of SPAE with a baseline method and find that SPAE tokens demonstrate higher semantic scores and improved reconstruction quality as the number of layers increases. Section. Token Pyramid Visualization. We're going to discuss a method of visualizing the tokens generated by the SPAE model. This visualization is akin to a pyramid or histogram, showing the most frequently occurring tokens across the first 4 layers of the model. We also present images reconstructed from the 5th and 6th layers. Our observations from this visualization are threefold. Firstly, the tokens in the SPAE model are arranged in a pyramid-like structure, with each layer containing tokens that are semantically related to the image. The top layers, although containing fewer tokens, seem to capture the main theme of the image. For example, in one of the images, the token presso, highlighted in orange, represents an espresso machine, while other tokens like blender refer to related objects. The 3rd and 4th layers provide more detailed information about specific objects in the image. For instance, the token thermo refers to a thermometer in the top left corner, while stove is found in the bottom right area. We also noticed that verbs related to the objects also appear, such as pouring, refill, spill, and brew. Secondly, we found it interesting that the CLIP model only uses English vocabulary. However, the SPAE model, thanks to its multilingual vocabularies and embeddings from the LLM, can map similar concepts in other languages. For example, the Dutch word koffie and the Danish word café are both mapped to the English concept of coffee. Thirdly, we noticed that the SPAE tokens, like the RQ tokens, can progressively refine the image's details as more layers and tokens are used. The 5th layer starts to produce a reasonable reconstruction of the image, and the 6th layer further improves the detail and smoothness. We also conducted qualitative studies to explore the ability of a frozen PaLM 2 model, which is trained only on language tokens, to perform multimodal tasks using in-context learning. We used a 2-stage decoding process for image generation. The first stage uses AR decoding to produce the first 5 SPAE layers with task-specific conditions. The second stage uses a task-agnostic NAR decoding process for the 6th layer, conditioned on the first 5 layers. We tested this approach on 2 tasks involving visual text reasoning, image captioning on Coco Captions and visual question answering, VQA, on Coco QA. For both tasks, we provided 10 unique training examples as prompts. In the VQA task, 10 different answers were presented to form a 10-way one-shot setup. We compared the performance of the SPAE model to a baseline model trained with the same frozen language codebook but without the proposed semantic guidance or pyramid SAQ. Our results showed that when the LLM is fed with baseline tokens, it tends to generate a caption or guess an answer based on the question alone. This can lead to inaccurate results. Similarly, if we only use the first 2 layers of SPAE or 5 words to represent an image, it provides insufficient context for captioning. Reasonable captions start to appear with 4 layers or 85 words representing an image, while complex scenes may still need the full 6 layers of 597 words. Section summary. The token pyramid visualization of the SPAE model reveals that the tokens are organized in a pyramid structure, with each layer containing semantically related tokens to the image. The top layers capture the primary theme of the image, while deeper layers provide additional details about localized objects. Furthermore, the SPAE model's semantic guidance allows it to map to similar concepts in other languages, and the use of more layers improves the image reconstruction with progressively refined details. Section. LLM generating MNIST images. We've been working on generating images of handwritten digits using a language model, specifically the MNIST dataset. We trained our model, which we'll refer to as the frozen LLM, using 50 examples of digit images. Each example was described with a phrase like, an image of K, and then represented by a series of tokens that correspond to an image of the digit K. This training was done using a method called SPAE. Once trained, we could ask our model to generate images in response to questions. For instance, if we asked for an image of 1 plus 7, the model would generate a sequence of tokens that, when decoded by SPAE, would produce an image of the digit 8. We tested the model with more complex questions that required mathematical reasoning or common sense, and it was able to respond correctly. The images it generated were unique, not just copies of the examples it had been trained on. This shows that our model can reason across different types of data, like text and images. We also explored using our model to generate images based on certain conditions. To our knowledge, no one has successfully done this with a frozen LLM before. We set up a simple experiment where the conditions were integers from 1 to 9, and the target images were created with different transformations like brightness, contrast, saturation, and color. We found that our model could interpolate the variable property when given images 1 to 4 and 6 to 9 as context to produce image 5. We then moved on to a more challenging task, generating an image from a condition image. This involved tasks like image outpainting, deblurring, inpainting, location translation, rotation, and so on. To generate images for each task, we used 10 pairs of examples with different levels of noise, ranging from 50% to 20%. We compared the results of different decoding strides and found that a single-step decoding with an infinite stride failed to produce a reasonable image. This highlights the importance of our proposed progressive generation technique. In the first stage, we saw improved quality with smaller strides down to 4. However, a stride of 1 was suboptimal due to the loss of context. In the second stage, most trials produced reasonable images, and we found that a stride of 16 struck a good balance between efficiency and quality. Section summary. The section describes how a frozen language conditioned image generator, LCIG, is able to generate images based on text queries and conditions. The LCIG is trained on MNIST dataset and can generate digit images based on queries like an image of 1 plus 7. The LCIG is also capable of conditional image generation and image-to-image denoising generation tasks. The progressive generation technique proposed in the paper improves the quality of generated images. Section. Generating image and text using a single model. We're going to discuss how a single language model can be used to generate both images and text. This process involves first filling in the central part of an image using a technique called in-context denoising, and then creating captions for the newly generated image. For a more detailed explanation of the inputs used in this process, please refer to the appendix. Next, we'll talk about converting images to videos using a denoising technique. Unfortunately, due to space limitations, we can't show the resulting videos here, but you can find them in the appendix. Now, let's move on to our ablation studies. These studies were conducted to test the effectiveness of the designs we proposed in our Semantic Pyramid AutoEncoder, SPAE. We evaluated these designs based on their reconstruction quality and semantic similarity. We used several metrics for this, including Frechet inception distance, FID, inception score, IS, learned perceptual image patch similarity, LPIPS, and contrastive language image pretraining, CLIP, and relative CLIP. We made several interesting discoveries during these studies. First, we found that using a fixed codebook without any semantic guidance negatively impacted the reconstruction results. However, when we added semantic guidance, the results were comparable to those achieved with the original Vector Quantized Generative Adversarial Network, VQGAN, and we were able to produce meaningful words. Second, we found that using a fixed codebook negatively affected the reconstruction quality when using the reparameterization trick, RQ. This is different from the standard setup where the codebook is learned. Finally, we found that the semantic autoencoder with quantization, SAQ, improved both the quality and semantic similarity of the reconstructions. The pyramid structure added flexibility, allowing for dynamic adjustment of the token length. This balance between high-level semantics and low-level appearance details was beneficial. Section summary. The section discusses the use of a single model to generate both images and text. The model first inpaints the center region of an image using in-context denoising and then creates captions for the generated image. Ablation studies were conducted to evaluate the effectiveness of the proposed designs, showing that using a frozen codebook negatively affects reconstruction results, but with semantic guidance, it performs comparably to the original model while producing meaningful words. Additionally, the use of a pyramid in the model improves both quality and semantic similarity by allowing for dynamic adjustment of token length to balance high-level semantics and low-level appearance details.